Good afternoon.
Sorry for being late. Had to do the bio thing. Between sessions. And the fun stuff today. Well, it's all fun stuff. Looks like we're missing a couple, so hang on a minute.
Nice, repping the company polo today.
Oh yeah, I had a client meeting, so it's always nice when there's tons of people. I think there was like almost 40 people on this meeting this afternoon, so everyone has their cameras on. You like to know who's who. But our marketing folks wanted us all matching, so. Of course, me, I'm the smart a-hole person that I'm like, well, we're not really matching because you guys are business people and I'm technical and we speak a different language. So I like teasing him. And of course that turns into, well, you don't know how to balance a checkbook. And I'm like, well, is it I don't know how or I don't care? They're referring to engineers being expensive, and costing lots of money, and having no sense of cost for parts and things like that.
I mean, they are right about us being expensive.
Yeah, that's right.
Not as expensive as bad business decisions.
I think their simple minds skew it differently. I think they figure out that if they just hit the right business model, they'll be like Elon Musk, and it's worth any risk. That's my impression of business folks, right? I don't know what's better to make fun of, business people or art people. It's a toss up. It's funny because I'm dealing with an architect right now for something in my personal life, and my wife has a hard time communicating with him, and she's like, I don't understand why he communicates like that. You guys are, you technical people. I'm like, no. He's on the artistic scale. Don't put him in our category, please.
Ouch.
Not in a bad way. I have respect for people in that, artistic. It's just not me. Okay. All right. So we are talking about something really cool. Hey, so what color popped up last time out of the gate? Was it red or green?
Green.
Green.
I think we're going to get rainbow today. Let's see. Yeah, it is. Huh. I wonder if they're like programming something to make it a different color every time. So weird. So last time we left off with this integration rule thing. And I said that we needed to come up with a way to integrate it, right? With this thing called a numerical quadrature. So it's an numerical integration rule. So that's where we're going to kick off today. And this is where I give you the punchline that we're not integrating at the nodes. So we have a, sorry. Numerical integration. Okay, so the idea is we have some function -1 to 1. We're in this C space. And I don't remember what I drew last time, but it doesn't really matter. It's just some function of C. It could be a function of X, but we're in the C space. So if we're in the C space, are we in where are we at? Are we
Local?
we're local, right? So we're in a local coordinate system, but we're like in a sublocal, right? Because we have global coordinate, we have local coordinate, and then we have local mapped to this C space. So it's kind of like this subdomain of our local coordinate system. So it's
Was it like the a coordinate system for the individual node you're looking at the local space?
has nothing to do with node. It has to do with being in that separate space. So when we first introduced it, it was based on an element. We had an element with node 1, node 2, and this was element 1, right? And this was in the X domain. And then we're mapping to -1 to 1 in this C space. So we're mapping the nodes, we're mapping the element. So this is still element 1, but it's element sub C. So we're in this a local coordinate system, but we're mapped also. So we're still in this mapped local coordinate system. And I gave you this integral of basically, we're going to looking at the integral from -1 to 1. So from, here -1 over here to 1 of this function C dc, which is approximately equal to the sum of k is equal to 1 of the number of sampling points, NSP, this WK, which this is a weighting function, F C of K. And let's kind of write out. So this is what we're going to try to do. And we have a couple of steps. And it's like we have 2 steps. So number 1, suppose that our function f of c is well approximated by the leading terms in some series. Yes. Like a power series, for example. So we have some function, you can approximate it with the first couple terms in that power series. So it's something like this. F C is equal to F naught plus F1 C plus 2 C squared, da, da, da. So that's kind of what that is. And 2, set this C sub k comma WK for a given number of sampling points such that as many leading terms in f of c's series expansion as possible um, are exactly integrated. So we have this integral from -1 to 1 of our expansion. dc is equal to the sum k equals 1 to the number of sampling points of our weighting function wk times our series we want to choose ck wk so that the equality holds for as many leading terms as possible. So here's an example. So I'm just going to show you kind of examples for this to kind of what's going on. So this is called a 2-point rule. So NSP is equal to 2. So for this, we're going to have a f of 0. We will have 2 is equal to W1 plus W2. For F1, we have 0 is equal to W1C plus W2C. F of 2, 2/3 is equal to W1C1 squared plus W2C2 squared. F3, 0 is equal W1C13 plus W2C2 cubed. And this whole thing leads to a W1 is equal to W2 is equal to 1, and a C1 is equal to a minus C2, which is equal to 1 over square root of 3. This right here refers to a 2-point Gaussian GAU SSIAN 2-point Gaussian integration rule. And what it's doing what we're doing is we have this C space, right? From -1 to 1 in C. And let's say that from here to here, -1 to 1 is an element, right? We did that before. And if we went back over here, this is our unmapped element in our X space. So this is X1, X2. So in our C space here, we have an element number 1, and we have 2 nodes. Okay. And we talked about once before that these 2 nodes have this thing called shape functions, right? That relate these nodal values. So at the node, it's equal to 1, and then at the neighboring node, it's equal to 0. So we did that, and those were these N1, N2 shape functions. What we're talking about is different. So that was a type of weighting, right? We did those shape functions to solve part of our problem. But what we're doing here is for this 2-point Gaussian integration is what we're stating here is for a weighting factor of 1, weighting factor 1 is equal to weighting factor 2 is equal to 1. What we're saying is that for a weighting factor equal to 1, that allows this power series expansion to exactly integrate for the first couple of terms. So what I have shown here is 3 terms, right? F of 0, F of 1, F of 2 is exactly equal to the sum of this weighting factor times those values. So what we're saying is when this weighting factor, W of K, is 1, what we're actually going to get out of this, if you solve this, is you're going to get this, that C1 and C2 are actually equal to, or minus C2 is equal to 1 over root 3. So what that ends up doing is this weighting functions end up being like here and here. So at 1 over square root of 3 and minus 1 over square root of 3. So you guys kind of following this conceptually? We're not at the node. We're in between. We're close to it. We're 1 square root of 3 away from our new coordinate system. That's kind of where we're at. But this is this is where this integration is actually going to get carried out.
Sorry, so I just want to clarify. So we only go to the sublocal space to solve the integration. That's why we're in the C space.
Yes.
And then, okay. So the X, that X element is in a local space, and we go to the C space to just for the integration, and then back to the local. And then we use a basis function to get our basis vector to give it to the global.
Yep.
Okay.
Yep. So right now, what we're trying to figure out is ultimately what we want to do is we want to figure out what the displacements are at these nodes, right? That's what we want. But we can't integrate this function right here directly, or our previous function. We can't integrate that directly. So we have this integration rule that says, well, if you break up your function into a power series or a Taylor series or whatever you want, and you can exactly integrate the first couple leading terms of those, because we know that those are the ones that are important. All the rest of them are just noise, right? If you can exactly integrate those first terms, then you're golden. But let's put this weighting factor in front of it. We need to put this weighting factor in front of it. So this holds true to make that power series work for the first couple of terms. So this is just an arbitrary value that we're figuring out. And a lot of times, to be honest, it ends up being 1, like we did here. And in fact, I think all of the ones that we do, no, they're
So
not.
the weighting factors are just to help you equate the approximate with the exact.
Exactly. That's all they are. The first few, and when I say few, I'm not giving an exact number. It could be the first 1. It could be the first 2. It could be the first 3. It just depends on what's important to you as the person developing a finite element code, how many of those terms you want to do it, or how complicated you want that.
Now, how do you, if you can't really integrate the left side of that, how do you know that those weighting factors make it equal the left side?
Because you've worked it out ahead of time. Ultimately, what we're talking about is element formulation right now. This isn't going to be something that is part of the finite element solution. This is going to be something that's hard coded into your finite element code for an element formulation. So if you picked a one-dimensional element with 2 nodes, it would be predetermined that your integration points are at 1/√3 and -1/√3.
Okay, so those have all been, the weighting factors have all been worked out on what you need to equate with the left side already.
Yeah, and that's where this is a little, there's a little discontinuity. This numerical integration is not something that you're solving while you're solving the boundary value problem. It's independent of that. It's part of something that would be hard coded into your element formulation. In fact, some of these that I'm going to show you today, people actually got their PhDs for coming up with the weighting function to figure out the integration points. This is something that's hard coded. It's considered an element formulation. If you pick a 3-node TET for some reason, a 2-dimensional trie or something, these weighting functions and ultimately the integration locations, those are predetermined by the code. You can't modify it.
Yeah, okay, that makes sense.
Right. And that's what we're talking about, is that kind of subroutine, or it's not even a subroutine, it's hard coded, it's already figured out. The point is we're going to carry out this integral at these locations. We're not going to carry them out. This is actually a pretty good point. We're going to carry them out at, I don't know, wherever it is, at 1/√3 and -1/√3. So you should be asking yourselves, well, what the heck? Because we're supposed to be integrating from -1 to 1, right? We're not integrating everything. We're leaving all this on the table. What's up with that? How do you think we're going to figure out how we're going to get from here to here?
Is a predetermined fudge factor you add afterwards?
No, it uses like linear interpolation. So this is why, and Jacob, for those of you that don't know, it works for Siemens. We ran into an issue a couple years ago now with one of our colleagues doing an assessment for something, and he had a really high stress at a node and couldn't figure it out. This is why, is because the solution wasn't solved at the node. It was solved at an integration point further away, and it extrapolated out to the node, which give it some ridiculously high value. And it
I remember talking.
It created a discontinuity.
Yeah. Integration points. Yeah, that makes sense.
That's what this is about. Because now you have to think that you might have a neighboring element next to this that has, right? Because this is just one element. More than likely you have another element in a node here with with 2 more integration points, right? And you have this function, and let's say that this function is the same. It's also going to calculate a different point, and it has to linear interpolate out to wherever this boundary is between the two, at the shared node. So if you have a disconnect there, it's going to average the values more than likely, and it's going to give you something totally bogus. So good luck taking a nodal value and trying to back out to what it is at the integration point. So it causes a lot of error. Not a lot of error, but it creates confusion with people that don't understand this, that haven't been exposed to it. If you have like a closed form solution and you're trying to compare it next to like a nodal solution, like what are the nodal displacements and stuff, and it's like, this just doesn't working out. Well, that's why, is because the solution is, the boundary value problem is ultimately solved not at the nodes. It's solved at these integration points inside of your element. And then you have to extrapolate the values out to the node. So
and the coarser your mesh, the further away it's going to extrapolate. And
exactly. So this is a 2-point rule. So it's a single element, one-dimensional element with 2 nodes. And I'm going to kind of give you kind of walk through a couple of very, very common elements, so you know what the integration rules look like. So for a 3-point, let's go back to black. For a 3-point, we're still in a one-dimensional. So this is a single element with 3 -1 to 1. We're still in the C space. And in this particular one, we have 3 integration points. So before I even talk about this, what's going to be the difference between a 2-node and a 3-node? Can you see that a 3-node is going to give you an intermediate displacement between the 2 endpoints? So if we look at a 2-point, what can happen between here? You can't get much fidelity between this point and this point, right? You could get, something up here and something down here. It can be kind of wonky. And then you integrate back to it, if you find actually a displacement to it. Having this third value here gives you some extra fidelity in here, right? Because maybe it's up here. So it's here to here to here to here. You get better resolution out of it. So the more points that you have, it's not talking about number of nodes. It's talking about the number of points within the element that the integration is carried out. And that's a huge misconception, that folks think that the integration for a finite element code is either solved at the element level or at a nodal level, and it's not. So for a 3-node, this value over here is -5/9. The center one is actually, sorry, it's not right. It is square root of 3/5 minus square root of 3/5. And I think if you want to look at this differently, it's roughly -5/9. And this one, the center one's not quite in the center. 8/9. No, that's wrong. That's a different one. Something else. Yes. Let's go with this. -√3/5 and √3/5 in the center, for your intents and purposes, is used the same as that center. So for a 2-dimensional and a 3-dimensional numerical integration, generally you must know the shape of its domain, of the domain, and it should be simple.
So domain as in like your A to B.
The shape of the element. I'm gonna
Oh,
draw
okay.
it right now. Yeah, it's talking about the shape of the element. In 2D, you guys already seen this. -1 to 1. It's a coordinate system there. And when I say simple, there's actually, if you guys get bored sometime and you want to look it up, this is actually a mathematical term, simple, that you can, or a geometrical term for looking at that. But typically you want ratios that are like perfectly square, or you could have ratio, perfectly square where all sides are equal are ideal. Or if you have like a triangular shape, 0, you want to be 1 and 1. Before I go on, what you want to avoid is weird stuff. Like you don't want an element like this, right? Or this, where you have really weird aspect ratios and things like that. And you can probably see why now, right? If our integration is set up on ratios and you're integrating like here and here or something, you're missing a lot, and it's going to be hard to get good data out of it. So ideally, it's a perfect square, or if it's a triangle, it's simple. So for a two-dimensional Gaussian, it's considered a 2x2 Gaussian. It's a 2x2 Gaussian integration rule. This assumes a perfect square element. So this is an element. The element could have as many nodes as you want. They don't really matter. So I probably shouldn't draw these in here for right now, but let's assume that, these are the nodes. And it has a W1 equal to W2 is equal to 1. This is our space. It's actually going to give us a 4-point integration. And this is going to be 1 over square root of 3. And this is minus 1 over square root of 3. And this one is minus 1 over square root of 3. And this one is 1 over square root of 3. And you can figure out the other. Now, so you can see that we're integrating within the body of the element. We're integrating in 4 spots. So if you wanted to know what's going on in this, say this is 1, 2, 3, 4. If we wanted to know the average result, I guess average is not a good word, the mean result, the average result of x1, x2, x3, x4. Those aren't really x's, they're integration points, but hopefully you get the gist of it. Comma, comma, comma. We would do that by basically saying integration point 1 plus integration point 2 plus integration point 3 plus integration point 4 divided by 4. And that would give us the average of whatever this integration is, right? It's a displacement. So it would give us the average value. This would give us an elemental value of what's going on here. So we'll figure out what from an element level, and you guys know what I mean by an element level, right? I'm talking about this whole square. We're calculating, we're integrating at each one of these locations, and we have an average value. Now, what if I wanted to know just this value? Well, I'm gonna have to interpolate what this is based on results from all 4 of these. It's not just a simple averaging. This would be a nodal value. So that's different than what this is, than what the average is. Okay. So now for a 3x3 Gaussian, example 3x3 Gaussian, and rho square we're going to have 9. So this one here is going to have a weight equal to 5/9 times 5/9, which is 25/81. The center one is equal to 64/81. This guy here gives us a weight of 5/9 times 8/9, which is 40/81. And then the specific values for these are √3/5. This is the 0 line. This is minus √3/5. Minus √3/5. 0 and √3/5. So 3x3 Gaussian gives you a 9. Okay.
And you said that's node independent, so that could be a 4 node or an 8 node, and
Yep.
still have you can still choose the 3x3 or 2x2.
Yep, it's node independent. It's part of your element formulation. So like when you're in ANSYS and you're like, yeah, I'm going for a 20 node. Yeah, it's not really bragging rights. You have a lot of nodes, but you know how many integration points are there? Usually there's a correlation in the element formulation of how many integration points are there, but you're not guaranteed. So if you were to look at a 4 node element like in ANSYS, you're not guaranteed that the number of integration points is the same as a 4 node element in SolidWorks or Abaqus. They're independent of each other. It depends on the element formulation. Okay. But in general, I don't want to write this out, but you guys can write this out if you want to. In general, for triangular elements, we return to the two steps, right? To seek optimal locations and weights so that as many terms as possible in two-dimension power series are exactly integrated. So we kind of mentioned that over and over and over. So now I'm going to kind of summarize what an element formulation is. And it is exactly what you just brought up, Jacob. An element formulation is how many nodes, what are the shape functions, and what are the integration rules. It's those together that kind of define what an element formulation is. So an element formulation is three things: shape functions, usually defined on a parent domain and then mapped it consists of a mapping. Remember the isoparametric mapping? A mapping of the parent element or the parent to the physical element. And this is usually isoparametric. And the third thing is an integration rule. On the parent element. Now, do you remember which one is the parent element? Is that the deformed element or the undeformed element? Remember, it was backwards. In the X space, you assumed a deformed element. In the C space, it's undeformed. So the parent domain is considered the undeformed space. That's where the integration rule is carried out on the parent element.
Can you repeat that one more time?
No,
I think
it's backwards. Yeah. So physical element is our X domain. Parent element is our C domain.
Where C is the deformed.
So shape functions, we define those in our parent domain. So our parent domain is being the C domain, is where we defined our shape function, right? And our integration rule is carried out in this C domain. But the physical element is our X domain. So it's a little bit backwards when we're thinking.
So the C domain is where we carry out or where we map the integration points, but then we have to map the C domain to a subdomain to actually solve the integration.
No, we're solving the integration in the C domain. We're getting the result, and then we're mapping back to the physical element to the X domain.
But because above it says you're going from the parent domain and then mapped. Are you saying and then mapped to the physical? That's why it seemed like you have three things, like a physical and a parent.
Well, remember, we're mapping twice. We're mapping more than that. We're mapping from a global domain to a local domain. That's like a change of basis.
Right. Yeah, change of basis.
Right? So that's a change of basis to get to that local coordinate system. And then once we're in our local coordinate system, then we're going to map to that C domain.
Right.
Do all the stuff in the C domain, and then we're going to map back to the X domain. Well, the X domain is considered the physical element. So when we went from global to local, we're at a physical element.
Okay, so that top line where it says shape function is usually defined on the parent domain, and then mapped. You're saying it's and then mapped to the physical domain.
Mm-hmm.
Okay, that's where I was. Okay.
Mm-hmm.
Okay.
Yep. Yep. So those are the three things that make up a formula element formulation. It's been a long day. Shape functions, isoparametric mapping, and an integration rule.
Now, sorry, one more. So when people talk about linear elements versus quadratic elements or even higher order polynomial elements, are they changing the shape function with those, or the so I didn't think it was I thought like the linear versus quadratic was separate from shape functions.
So it could be a lot of things. It typically means the shape function. It typically means the shape function of why they're doing that. Because if you remember, I'm going to slide this to the side because I don't want to change things. So if you remember, for our shape function for a single element, we said that it's at this value of 1 here, and then it has to go to 0. You would agree that this is all linear, right? But when we went to, so this is a single element, and this is still a single element. This is one element with 3 nodes. So the shape functions are node dependent. But for that rule to hold true, where the shape function has to be 1 at that value, and then linearly decreases at the neighbor node, it's nonlinear from that node to the next to get to the
yeah. Sorry, I was misremembering. I thought the 4-node quad element had nonlinear curves, but those were also linear from element to element.
Yeah.
Okay, that makes more sense.
Yeah. So this would be considered nonlinear shape functions.
Right. Yeah. That makes sense.
Yeah. So when somebody says, you're actually digging exactly where you should be digging, Jacob. When somebody says, I have a nonlinear element formulation, well, you really should ask, is it the shape function? Is it the isoparametric mapping? Or is it the integration rule? Because now you can see that any of those you could have a nonlinear function in it, right? Because the way we defined our shape function is right here. You could have a linear shape function, or you can have a nonlinear shape function. Our isoparametric mapping, that's pretty straightforward, but I don't know, someone could come up with some weird mapping that didn't quite get you. I mean, I could imagine that, this is -1 and this is 1, right? And we said that our integration rules were here and here at, I don't have them in front of me. Was it square root of 3/5? 1 over root 3? 1 over square root of 3 and -1 over square root of 3. I don't know. Somebody might decide that, they don't want their isoparametric mapping to go from x1, x2. Maybe they don't want it to map node to node. Maybe they want to do something funky and they want to map a node to an integration point or something. That right there is not going to be, more than likely, that's not going to be linear, right? That could be a really weird it wouldn't be an isoparametric. It would be some sort of custom mapping to go from parent to physical domain. So you can have some nonlinearities there, but definitely in the integration rule, that was just some arbitrary weighting factor that we came up with that allowed the first couple of those power series to be exactly integrated. What if somebody wanted to find weighting functions that made, out like 10 or 20 terms? More than likely, you're going to have to get a little bit more complex with those weighting factors, and they're not going to be linear anymore. So it's almost meaningless when someone says that unless you know these three things: shape functions, the mapping, and the integration rule. So I have a couple of kind of generalities for you. General notes. This is more for when you're actually using a finite element code. So general notes on elements.
Hey, Professor, could you clarify that the parent domain is the undeformed item?
No, the parent domain. Yeah, the parent domain is undeformed.
All right, thank you.
Yeah. So for here's a four node. It's called a 4-node quad. 4-node quad. And this one's 3-dimensional. And we have mu, C, and this one is zeta. And we have so 4-node quad element. So 4-node quad element. So when I say that, I mean like one side of this could be an element with 4 nodes, but that can be extrapolated out to, I didn't do that very well. There's another node in the corner, in the bottom corner. So if you were to look this in 3-dimensional, you would have eight nodes. So you'd have 1, 2, 3, 4, 5, 6, 7, 8. So you would have shape functions. How many shape functions would you have? In this particular one, we'll have 8 shape functions. 1/8 is 1 plus C. I'm not going to write all these out. 1 plus It's not C, that's theta. Actually,
So you're talking about for that whole 8-node brick, there's 8 shape functions, or for just a
no,
two
for a
node-
four node, for like one of these sides, for
just
one
one?
side. Yeah. They're basically put together, so you could have multiple. So you could have, so for integration rule, probably shouldn't have drawn this image here because it's confusing. So for an integration rule, maybe I should do this. For node quad, can be turned into 8-node cube. Shape functions per 4-node quad. Okay. And for an integration rule, again, for a 4-node quad, it is typically a 2x2 Gaussian. For a 8-node cube, it's typically a 2x2x2 Gaussian. This is what's most common. But lazy codes may use 1 point. Don't use these elements. They are junk. Hopefully that's explicit enough. Hopefully you can see that if you had an element like this one right here, this 4-node, 2-dimensional node, and I told you that we were going to integrate this thing in one spot in the middle, good luck getting anything reasonable for reasonably accurate at these node values by the time you extrapolate it out, right? I mean, I guess it depends on what your mesh density is, if it was really, really small. But you can always swing it time. So I have another one here. So for a 3-point trie, one, two, three. Shape function usually sits right around here. I mean the integration rule. So shape function. Integration rule. Is considered a 1 point at 1/3, 1/3. The weight is equal to 1/2. This is a horrible element. Very poor approximations. Not ever recommended. To use. Does anyone know why a finite element code would actually include something that I'm actually stating here that is horrible and you don't want to use it?
It's easy to make a mesh.
It's super easy to discretize a potato with triangles. And it's super fast to solve if you're only integrating one spot in that thing.
Where are the integration points for like a trie element that would have like a more advanced trie element that is better formulated?
I've got a couple. I've got a couple more I'm going to show you. I've got a 6-point trie, a 9-point quad, an 8-node serendipity that I'm going to show you still. So, oh, we only have 10 minutes left. We're not going to finish. So that's actually the next one I was going to do, a 6-point trie. So 6-point trie. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. The numbering is always, it always goes in this direction, starting at your 0.1, and you go to the major intersection, geometric intersection, 2, 3, and then you come back to the closest one to your 0 here, going in that direction, and you go and you continue your number 4, 5, 6. If we had a middle one, the middle one in the center would be 7. So that's how that sorts out. So this one's usually a 3-point integration, and I don't have the actual location sorted out, but it's a 3-point. Three-point integration is typical. A 9-node quad. So this one numbering is 1, 2, 3, 4, 5, 6, 7, 8, 9's in the center. It's usually a 3x3 Gaussian. Shape functions. Are products of Lagrange polynomials. Like the n to the ninth is 1 minus c squared. You can typically look these things up if you want to see them, but the Lagrange polynomials were, if you remember, -1, 1 at 0, 1. This is one that we drew before. These are completely, they can be completely nonlinear, but they're typically linear to here, drop down. So just like we just looked at a second ago, up to 0, up to the 1 point, back down. So this one right here is the 1 minus c squared. So when I say products of Lagrange polynomials, you know, you just have to sort it out for what that is for each one of the legs.
Professor, was there any reason why you went counterclockwise on the 6-point trie and then you went clockwise on the 9-point on the count?
I didn't, because here is the origin on this one.
Yeah, origin base, got it.
Yeah. Yeah, integrations on this one could be, you know, they could be different. They could be different ones, but you could have, I'm not gonna write out what actually, you could have an integration at the node, that center node. It could just be a 4 integration point, but a 3x3 Gaussian is this, right? So this would be one we would actually be integrating at that center node. A 27 node hex, 27 node hex or brick is the 3-dimensional version of this. There is one called an 8-node serendipity element. 8-node serendipity. And my professor at Davis that studies finite element, has his own finite element code, loves this one. It's the same one that we did before without the center node. His claim is that it is way faster solution time and does not sacrifice much resolution in the displacement field. And it's typically a 2x2 Gaussian. So this one comes highly recommended. Very efficient.
And that's only in his code.
No, it should exist. I know it's an Abacus. Jacob, do you know if this is an ANSYS?
I think my understanding was that I think that's used in other places, but I could be wrong. I could have missed that there was usually a center node also.
So Yeah, so if it's a center node, it's not serendipity. I don't know who named it serendipity, but he says that's a common. I haven't seen it in any of the ANSYS help files.
So
I
this
looked up
basically,
Not by the name anyway.
I looked up the default ANSYS try element, and it has 3 integration points by default for the try.
Mm-hmm. Mm-hmm.
And then unless there's plasticity, then it uses five integration points.
Okay.
so would this basically classify as like a quad 8?
As a what?
As a quad 8 element? So
Yeah,
quad,
it's an 8. It's an 8 node element. 8 node element. Using a 2x2 Gaussian integration rule.
Yeah, I think quad's usually used for the number of nodes, not the number of integration points. If you usually hear people say quad.
Yes. So when you hear the word quad or things like that, it's referring to nodes.
oh, not integration points.
Well, it's actually referring to quad is referring to the shape. It's a square. 9 is referring to the number of nodes. And then integration rule people like never talk about unless you're like total nerds like we are taking this class. Like people that have used finite element codes and stuff for a long time, if you talk to them about integration rule, I've seen them gloss over. They don't know what I'm talking about. So they know about an element, they know about nodes. They don't realize that the integration is actually carried out somewhere within the element and it doesn't correlate to the number of nodes. So you guys have a leg up on that. So if you want to go apply for a job at Abacus, you'll have a leg up. Okay, I think that's a good stopping point because the next thing has a little bit of writing, but I'm basically going to explain how do you decide what the integration rule is, right? Of course, there's rationale with what we should use. And it has to do with the stiffness matrix. Cool?
Yeah.
All right. Yeah.
I'm kind of curious. So this is I guess is a little bit like outside of the class-ish, but not really. So usually when I try to mesh and I get an error saying there's a certain number of elements that have errored in Nastran, it'll pop out analysis error right away. So is that kind of correlated to this topic that we're talking about right now?
You mean you're getting an error just from meshing?
Yeah, so like some of the elements will be extremely skewed. And
oh, so that means that the finite element program that you're using is telling you that you're getting really strange elements. You want an ideal element is if a square, right? A 1 by 1 square, or a trie where the both legs are 1. You're never going to get that. It's going to tweak those lengths to get you to kind of fit the body. But you can imagine if you have, a shape like this, you're not going to exactly fit an element in here. You're going to have some error associated with it, right? You can't mesh this with a square because you have curved shape. So you're gonna have areas that you're not meshing. So it's going to try to fill those areas with a bunch of triangles and things like that. So it could be that you could have a discontinuity in your part that you don't see maybe in your model. Maybe if it tells you where the bad mesh is happening, you can look at your body. Maybe there's a problem with your model. I've had issues in the past. This was a long time ago where I had a part that I had modeled in SolidWorks, and I was trying to do an FE solution in ANSYS, and I was pulling the model in. Same thing, it wouldn't mesh, and for the life of me, I couldn't figure out why the heck it wouldn't mesh. And I had a sketch that wasn't fully defined in my SolidWorks model. And when I fixed that sketch, it meshed. I fixed the sketch, I re-imported it, and I didn't change any dimensions. I just fixed, why it was underdefined, fixed that, outputted the model and imported it. So I would check your model to make sure there's no errors in it, or there's discontinuities like parts, points not touching or something like that. There's a lot of reasons, but if it's skewed shape, I would try maybe changing the density, reducing the density. Maybe you do that first. I'm sorry, increase the density, so smaller elements, more elements. You can try changing the element type.
Okay, yeah.
Going from a quad element to a tri or whatever. I don't know if you have default set up or what it's trying to do, but there's a lot of little things you can do.
Okay, yeah, that makes sense. I was just wondering if that's like because I've like had shitty meshes before and then they just pop out like a solution still, but then with Nastran, it's like it forces you to get a good mesh.
Well, usually there's like a minimum allowable quality. So usually if it is really low threshold, usually if it doesn't pass that, there's something insanely wrong.
Really bad. Yeah.
Oh, okay.
Yeah. So there's
they
something
have like a
really bad,
like 200 to 1 or something like that,
mm-hmm.
or have zero area.
Okay, that makes sense. Yeah, I was like reading the script and I saw that. All right, thank you.
Yeah, remember we talked about this. If you had an element that did this,
yep,
it could have done something funky like that, and it rejects it.
Yeah. Okay.
Sorry, we're yeah, gotta put an extra that it's bad. Okay, well, have a good evening. Have a good weekend. For those of you that watch Formula One, it's Formula One weekend, so that's good. And I'll see you on Tuesday.